Our speaker for today is Professor Kaushik Roy. Professor Kaushik Roy is going to speak about rethinking computing with neuro-inspired learning. He's currently the Ed Tiedemann Junior Distinguished Professor of ECE at Purdue. He graduated with his BTech from IIT Kharagpur and then a PhD from University of Illinois at Urbana-Champaign. After that, he had a short stint at Texas Instruments and then joined Purdue University, where he has supervised over 100 PhD theses. In a fit of enthusiasm, I said 1,000, but 100, yeah. And he's been the co-author of 2 books on low-power CMOS VLSI. He's a fellow of the IEEE and also a distinguished alumnus of IIT Kharagpur. He's actually no stranger to the division of EECS. In fact, he was a member of the International Review Committee for the division of EECS about 5 years back. And it's a pleasure to welcome you back as a distinguished speaker and as the plenary speaker of the EECS Research Student Symposium.
All right, thank you very much. And really, it's a pleasure. And thanks for inviting me for this particular symposium, the 10th anniversary one and the other symposium that's happening here in ISC. So I'll take this opportunity and talk about some of the work that we've been doing. And the title of this talk is on rethinking computing with neuro-inspired learning, really geared towards looking at new workloads, the ML, the machine learning kind of workloads. So what I'm going to do is I'm going to talk about the entire design stack, going all the way from algorithm, circuits, and hardware architecture. So we all know that machine learning, deep learning has made a huge amount of progress in the recent past, right? And you open up any tech magazine or in fact even newspapers, you see a huge amount of news on AI. And some of these things are quite interesting. GPT-3 now, GPT-4 and so on. But one of the recent ones that came out in the CNN Business was quite interesting, where the title of that article was "AI won the art contest, and the human artists are furious about it." So what does it tell you? It really tells you that their AI is doing a really excellent job. But the question, of course, is while it's really doing an excellent job, there are still various challenges we have to take care of. As an example, if you really look at the biological system, and this is something that we've been actually doing some experiments on, certainly we have made a tremendous progress, as I mentioned, but the biological system still possesses a level of functionality that is unmatched in the artificial systems. And if you really consider the reactive behavior of a fruit fly, and interestingly, this fruit fly has about 100,000 neurons, they fly fast and really avoid obstacles. So if you really look at some of these, videos, when you try to swat a fly, it really moves away and moves away really, really fast. So it's very, very difficult to do that. So with 100,000 neurons, they can do it. And in fact, interestingly, what we did is we actually worked with one of our collaborators as a part of the Center for Brain-Inspired Computing that we had, Costas Danailitis' group. They actually implemented a drone with, they called it a flying monkey UAV. And interestingly, it doesn't certainly do the kind of things that a fly does. But the compute power of that is about 1 to 2 watts. Now, on the other side of it, if you look at the fruit fly, and again, really only considering the compute power only, it's about microwatts or so. There's a huge, gap, as you can see. And while still not able to do the kind of things that the fly can do. So, if you still further look into the efficiency gap a little bit further, what we did is we did a case study on smart glass with a state-of-the-art accelerator. So in this particular case, I'm showing actually a smart glass where one can wear it to recognize, for example, in this particular case, a flight attendant wearing it to recognize their important customers, and they give them the right kind of service that they require. It turns out, and if we did an analysis of it, implementing a retina and a DNN on this, on the smart glass, without going into the details of the analysis that we did, under ideal conditions, and this ideal condition is important to understand, that did not consider the display power. And that takes a good amount of power consumption. It turns out the battery life was about 1 hour under ideal conditions. Now, if you consider, all these non-idealities, it turns out the battery life is probably going to be half an hour or so. So the question, of course, is, why is it so inefficient? And we certainly have an existential proof that the brain is reasonably efficient. So with that in mind, if I were to really think about what are these inefficiencies coming from, turns out that the algorithms, first of all, we don't really know the exact algorithms that's in the brain. The second is the hardware architecture that these algorithms are implemented in. For whatever little that we know of the brain is not like a von Neumann machine, right? We don't have a CPU on one side and a memory on the other side. So it's the memory and the memory and the computer all mixed together in some interesting ways. And the computations that are done, we don't understand it well, but certainly not a von Neumann machine. Some computations in some ways, interesting ways, are done in the memory itself. And finally, the circuits and devices. The CMOS certainly is the workhorse, has been the workhorse of the electronics technology in a lot of ways, right? But they don't really can very well represent the neurons and synapses. I mean, I would say not quite effectively. So is it possible that I can really look at devices that can, or neuromimetic devices that can mimic the neuron and the synaptic operations better? So those are the kind of things that can potentially look at and, improve the efficiency. So to that effect, as I mentioned, there's a need to really look at this entire design stack, going all the way from algorithms, which includes the network architecture. And I didn't talk about the sensing part of it. Sensing is an integral part of this whole analysis that one needs to consider. And we'll go into a lot more details of sensing in a few slides. The hardware architecture, that turns out to be quite important. And finally, as I mentioned, the circuits and devices. So the question, of course, is can we really, since we know that the brain is reasonably efficient, so can we take some cues from the brain? And what are the different cues that we can potentially take? Hey, one can try to look at the neuron model. Now, in standard deep learning, we'll go into that. I mean, we use, in general, the ReLU-ALU, the ReLU activation. So is that the best one? On the other side of it, how about the learning algorithms? What kind of learning algorithm should I use? What's the network topology? And how about the computing principles, as I mentioned, that the computing in the brain is done in some interesting ways in the memory itself. So with that in mind, if I were to really think about the neuron model, I can look at a biological neuron in this particular case, which is a leaky integratin fired neuron. And if I do have a bunch of inputs which are coming in, which are shown right here, the membrane potential of the neuron goes up. And if there are no spikes, then the membrane potential goes down. If there are enough spikes and the membrane potential reaches a threshold, then the neuron spikes. And then I reset the membrane potential. On the other side of it, there are other kinds of neuronal activities that one can look at, stochastic neuron, more generic Hodgkin-Huxley model, and so on. What about the learning algorithms? And today's deep learning certainly use what's called the backpropagation. And if you're in machine learning, you're probably familiar with it. But backpropagation has a good mathematical, underlying good mathematics to show basically at the end of it, it actually can show convergence. Now, the interesting thing about the backpropagation is the fact that if I have a network, and if I want to learn, for example, dogs, right? Then I show the dog to the input to this neural network, and my dog neuron at the output should be active when I'm showing that. But if it doesn't, let's say there's something else gets active, then what I can find out is, hey, what's the loss? And if I can now take that loss and backpropagate to the circuit, and then update the synaptic weights such that I can actually, take care of the loss, in that case, I can actually learn. And that kind of learning is what, certainly today's deep learning networks do. But interestingly, there's been experiments done back in 1998 and by Bai and Pu, which actually shows in the hippocampus of rats, there's also local learning. And the kind of local learning that has been observed, you might actually be familiar with some of those. It's called, spike time independent plasticity, meaning thereby that when an output neuron spikes, what they observed is that, based on the timing of the output neuron spiking and the input neuron spiking, one can update the synaptic weights accordingly. And so that's called spike time independent plasticity, depending on the timing between the input spiking and the output spiking event. If the spiking event happens close to the output event, in that case, actually, you update the weights in a different way than if it didn't happen in a close proximity. On the other side of it, what kind of network architecture should I use? Should I really use, for example, a VGG16 or a ResNet, whatever, 50 network? Should there be backward connections in the network? What should it be? What should be the network architecture like? Should there be long-range connections, and so on? And finally, at the end of it, we also need to think about the computing principles of the brain. As I was mentioning earlier, one has to really think about, should there be tightly integrated compute and memory or not? How easy it is to be able to design that. Should I have asynchronous event-driven computations? And we'll see that if you really try to use spikes, in a lot of cases it does make sense to do event-driven computation. And finally, another thing that is also very, very important are the sensors, right? That basically tells you what kind of input what kind of input is going to be coming from the sensors. And again, we'll see that depending on the kind of input coding that is there or the input sensors that I use, it turns out the kind of network that I would use is also dependent on that. So with that in mind, if I were to now focus a little more details of the neuron models, and I was mentioning earlier, this is basically my spiking neuron model, where I have these input spikes which are coming in, the membrane potential goes up, and beyond a certain point, it actually fires and resets the membrane. That can be represented really by an RC circuit in a lot of ways, right? And on the other side of it, one can make simpler assumptions and say, hey, there's not going to be a leak. And if there's no leak, you can potentially think of a neuron to have an integrate and fire kind of operations. Now, leak in a lot of ways is kind of interesting and important. The reason is you can actually get rid of, for example, noise and other things using leak. Leak also helps in a lot of ways in forgetting behavior. But this is a simpler model that one can potentially use. And then if you look at the other way around, one can also use, for example, an activation function of the neuron to be a sigmoid activation function. The reason I'm showing this particular activation is that some of the devices, the neuromimetic devices of the neurons that we've been looking at, has this kind of behavior, which is actually a sigmoidal switching behavior. In this particular case, it's actually a stochastic sigmoidal behavior that I'm showing here. And, time permitting, we can talk about, for example, some of the magnetic tunnel junction kind of devices, which has directly a behavior which is like stochastic sigmoid function. And one can potentially use that for having a stochastic neural network. So that's another kind of activation. And finally, standard deep learning has been using ReLU neurons or, for example, tan hyperbolic or in fact even sigmoidal kind of neurons for different activation. Going into the network architecture into a little more details, but before that, I just wanted to mention that certainly we need to figure out what kind of activation function that we'd like to use. So now if I have to really think about the network architecture, our collaborator again in our center, Jim DiCarlo, they were doing some very, very interesting experiments. They were looking at the visual cortex of monkeys, and there's a good amount of work that has been done in the visual cortex. So what they did is they basically looked at the V1, V2, V4, and the IT of the visual cortex, and they probed the monkey to few of the neurons. Of course, they can't do it in all the neurons, and they would show, for example, this set of images. And if the monkey recognizes those images, then they'll be given some rewards. So then they would figure out where these activities are, the activities of these neurons are. They did some regression analysis and then looked at also today's standard deep learning. And those deep learning networks could be a VGG16, could be again a ResNet 50, and they tried to figure out, hey, is there a correlation that I can potentially find, and is the correlation higher in VGG16 or a ResNet 50 and so on. And if I could find a good correlation, they came up with a score called the brain score, and the brain score basically tells you how bioplausible, so to say, the network is. And what they found out is that there's a reasonable correlation between the brain score. The higher the brain score, higher was basically the accuracy. So that was kind of interesting. But and with that in mind, one can potentially think of designing new networks, right? New network architectures, which has quote-unquote better brain score. And hopefully those higher brain scores would lead to better accuracy. And to that effect, also people looked at network architectures like, CoreNet, they called it CoreNet, and that gives you, better brain score with a better accuracy. So that those are different, certainly possibility, and these are bioplausible networks. And finally, the computing principles, as I said, those are going to be quite important. So what I'm going to be focusing on now is really, what kind of input coding that's going to be important, because that is really going to be driving, or at least those are going to be input to my network architectures. So with that in mind, let's try to look at, and in fact, in all these cases, if I were to really look at this entire design stack, it's very important to really reconsider some applications. And to that effect, again, remember we talked about, flying like a fly. So if we want to look at basically that and say, hey, can I really do completely vision-based navigation? And in order to do completely vision-based navigations, the things that I just talked about, the network architecture, for example, the activation function that I need, the learning principles, or in fact, even the hardware that I'm going to be building, what should it be? So with that in mind, let's try to look at a very simple design of, it's not quite simple. If I were to have a drone going from point A to point B, what are the things it has to do, right? The first thing the drone, but if it has to go from point A to point B, has to figure out, and just like a human, if I were to go from point A to point B, I have to figure out what's around me. What are the things that are moving? So in other words, if I were to really look at the environment, there are pixels, and these pixels would have certain kinds of, how are the pixels, getting, rather, the movements of some of those pixels. That's what I'm going to be interested in. So that's basically the task which is called optical flow. So I have to now figure out, going from point A to point B, what are the static objects, what are the objects which are moving, right? And then I have to plan my path, right? And avoid the objects. And finally, then I have to take the action of proper motor control so that the drone can go from point A to point B. And then I might have to also adaptively change my path planning. So the first thing the drone has to see is it has to see with a camera. So in this particular case, we're going to be looking at the DVS camera and the standard frame-based camera, and I'll go into that in just a minute. And then that input to that from that camera has to go into the network architecture that I basically talked about earlier. What should be the right network architecture? Should it be, for example, a spiking network? Should it be the standard ANN, right? Should it be an LSTM? And at the end of it, the kind of network architecture that you define is also going to be, in some ways determining what kind of hardware architecture that I'm going to be implementing things on, right? So to that effect, there's a need to also then think about, hey, the hardware architecture, should I really do computing in memory? And if I do that, do I get a large advantage or not? All right. So with that in mind, let's try to look at first the sensors. And looking at the frame-based cameras, this is basically the standard camera that we are all used to. For example, I have a video that's coming in at different times, and the input to that, coming from that camera can go into a standard neural network. I'm calling that standard neural network, the deep neural network, to be an ANN, meaning thereby it's an analog neural network. The reason I call it analog is not because I'm doing the computations in the analog domain, but the inputs are analog. And so if I take that, I'm basically in this particular case showing an encoder-decoder kind of architecture. If I do that, and turns out that this camera certainly suffers from certain problems. The problems are motion blur and high dynamic range. On the other side of it, one can potentially think of these event cameras, and this is an example of what the event camera is going to do. If the input video is somewhat like this, then the events, there are no events at this time, it has stopped, and what you see is like, zero output. However, if there's things which is moving fast, you can actually get outputs which are positive. When there's a relative motion between the camera and the object, I actually end up producing a spike. If there's no relative motion between the object and the camera, there are no spikes, right? So it turns out it's actually a bioplausible camera that was designed actually about a few years ago in Zurich. And this is the camera that is actually kind of interesting. The reason being, it produces spike outputs. Now, why spikes are important? Again, the spikes tells me if there is a relative motion between the camera and the object, right? The second thing the spikes also tell me is that how frequently these spikes are coming. And that also tells me the movement of the object. Is it going fast? Is it going slow? In what way it's going, right? And in fact, interestingly, if this camera, if you can take these inputs and if you have a network that can effectively utilize the spikes and the timing between the spikes, if it can utilize that effectively, then you can actually learn some of these movements. And that is something which is kind of interesting and important. And it turns out that I can actually now directly do it with a spike-based computation unit. So now if I have potentially think of, spiking neural network, and I have activation which is leaky integrated fire, I have my inputs which are going to be coming in, right? And if I can somehow take advantage of it and learn the timing between the spikes in an effective way, then I can potentially do a better job. This camera has better, that doesn't really have any motion blur, which you can see in the standard camera. But this one actually is that way much better, and you can have a better flow estimation, optical flow estimation. Few other things, I'll go into the details of it in just a minute, but I thought that it's very important to understand that, hey, one can, depending on the kind of inputs that I have, I can use the right kind of activation functions. Now, the second thing that is important is basically, hey, what kind of, I call it under the algorithms, hey, what kind of network architecture should I use? What kind of learning should I use? So to that effect, let's try to see, again, taking the example of the optical flow, what kind of network architecture can be interesting and important. So what is optical flow? As I was telling you earlier, you need to understand when when the drone wants to go from point A to point B, it has to understand the environment. And require understanding of the surrounding motion. So what is really going to happen is that this is the eye, and you have an object in front with a pinhole camera. So what you end up doing is you estimate you look around you. There are all these motion vectors which are 3D motion vectors, right? That would get mapped into a 2D motion vector, right? So in other words, the optical flow estimation of 2D motion field by computing the spatial and the temporal variations of the pixel intensities. And that would be optical flow. So if I can do that, it's an ill-posed problem. The question, interestingly, is the fact that, hey, can I use image processing techniques to do that? The answer is yes, and people have been using image processing techniques to do such optical flow. But it turns out that if you do optical flow using some of these neural networks, actually end up getting better results. And then this is just an example of some sparse and the dense optical flow that I'm showing. Now, in order to do the optical flow, without going into details, one can potentially use the network architecture, which is kind of like this encoder-decoder architecture that I showed earlier. Because you can have your input to be these images, and the output is also going to be an image. And so you can potentially think of an encoder-decoder architecture. So what we did in this particular case is, the first one that I'm showing here is can I use both cameras? Can I really use the DVS camera that I showed and the spike-based, the DVS and the frame-based camera at the same time? Now, why is that important? Now, if I were to really think about using spiking network versus a standard deep learning network, what's the difference? People keep saying that, hey, spike-based computation units or spike-based neural networks, they don't give you good accuracy. So in this particular case, you have to really understand what applications that I'm using it for. Now, a standard deep learning network, if I were to think about it, it doesn't have any memory elements, right? And you use ReLU as an activation as an example. So if you were to really think about it, it's kind of like a combinational circuit, if I may call it a combinational circuit. So now if you think about an RNN, what is an RNN? There's a feedback. So it has some sequentially to be able to capture some sequential behavior, right? So one can use an RNN for capturing sequential behavior. What is an LSTM? Actually, in fact, you can have feedback and some memory in it. So if I were to really think about it, it's kind of like a finite state machine that I have. And what would then be a spiking neural network without any feedback or any feed-forward connections? That would be more like a pipeline circuit, right? Because each layer of the network now has a membrane potential. And if it's an analog membrane potential, as the input comes in, the membrane potential goes up, stays there, right? Or leaks a little bit, and then you have more inputs that are coming in, and you keep on increasing it, leaking, and then finally at the end of it, it actually fires. So it's like a memory. And leak in a lot of ways is very, very interesting because just like an LSTM, where you have a forget gate, leak can help you also forget things, right? And leak can also help you in getting rid of noise. So with that in mind, probably it does make sense to use, for sequential applications, spiking neural networks. So what's the catch? The catch is training time. The training time is going to be longer than a standard ANN. Now in an ANN, if you really think about it, how would I use that information on timing? So one way of doing the timing information in an ANN would be, for example, if I do have these DVS camera inputs. So you have 2 frames coming in from your frame camera, and in between you have all these different spikes that are there because of the movement of the objects. Now, for a spiking network, ideally, I can take each of those time frames for spikes, and I can send it to this pipeline circuit, which is my spiking neural network. Right? I can't do that in an ANN. So in an ANN, what I end up doing is I take a few blocks of these between 2 frames. There might be 100 time steps, right? I break it up into 10 or 20 time steps, combine all the spikes together, and feed it into channel 1. The next one goes to channel 2, the next one goes to channel 3, and so on. So in parallel, I send it over to the ANN. Okay? And then I combine them together. The input is large. Then I combine them together. But unfortunately, the problem is that I still lose my timing information. But if I now somehow end up taking the spiking network, it can be a completely spiking network for optical flow, or it can be a completely ANN with different channels, as I mentioned. Or you can potentially think of having a network which has the best of both worlds, taking really ANN encoder with frame-based inputs, spike-based inputs which are coming in from the DVS camera, that's a spiking encoder, then combine them together, and really if you do the analysis, it actually gives you the best accuracy. Okay? Why? Because I can now effectively capture the timing information. So why did I even use my ANNs? It turns out, again, the pixel intensity information is also important. I can combine them together to get better optical flow. That's the reason it actually gives you really good accuracy. In this particular case, I'm showing an example of data set with about 7.5 million parameters. Now, one can also say that, hey, can I reuse a fully spiking neural network? Or a fully, ANN or a DNN kind of network? And if you do that, it turns out in order to get comparable accuracy, okay, we had to use about 13 million parameters. Now, this is also kind of interesting, is because of the fact that training also becomes a lot more difficult here, right? It's a completely spiking network, so training becomes more difficult. This one is a hybrid network, training becomes easier. Now, we can also think of, hey, can I really capture the timing information using very, very small networks? Okay? And in fact, what we really look at is FireFlowNet, which is a very lightweight network architecture with about 60,000 parameters. And in fact, it actually could give an accuracy which is reasonable. I mean, 2 or 3% less, but was able to actually do reasonably good optical flow. Can be potentially used in edge applications. Now, what I really wanted to underscore the fact here is that if you really want good accuracy, the hybrid networks are actually good, taking the best of both worlds of ANN and SNN. Now, if you want lightweight architecture for sequential tasks, turns out some of these fully spiking networks are reasonable too, because they can capture the information about timing, and with lot less number of parameters. So as an example, I'm basically again showing an adaptive flow, that same kind of architecture. The take-home message from here is that the endpoint error basically tells you what the optical flow error is. The lower, the better. So this is an example of doing completely ANN-based optical flow, and the blue ones are with very lightweight networks to do optical flow. Now, if I look at if I were to get the same accuracy as this standard DNN, I can actually use a much smaller spiking neural network with about 48x less parameters. Okay? still giving basically, again, the same accuracy as this. And of course, that translates into an improvement in the number of computations that are required. Now, that does not translate completely into the power consumption improvement, because if you end up implementing that in a GPU, you're not going to get that improvement. Because GPU is not suited towards really taking care of these computations. So you need a little bit different hardware to do that. But if you just look at the computation part of it, then it can actually give you a good amount of improvement. Now, going further from optical flow to segmentation, it turns out, again, you can do segmentation, again, with a very, very similar kind of hybrid network. And again, I'm not going to the details of it, but what I really wanted to underscore the fact that just because these two networks are, the hybrid networks are used with two different sensors in this particular case, again, vision sensors, you can sometimes be able to, in this particular case, I'm able to actually, there's a lamppost here which, both this, if we do separately the spiking networks or the DNNs, they don't detect it. But the hybrid ones does detect that lamppost. Again, not going over the results in the details of it, but most importantly, actually, it turns out that for segmentation, again, these hybrid networks actually do give you better accuracy, better MIOU, and with much less number of parameters. And that's something which is important, for edge kind of applications. And the reason why is because, again, taking the best of both worlds in some ways. Object detection. So far we have talked about optical flow segmentation, but let's talk about object detection. And what we wanted to do is try to see if I can do more bioplausible object detection. So the way we humans do it is using foveation and saccades. So if you look at the neuroscience community, they've been talking about what's called the two-stream hypothesis. And the two-stream hypothesis is that proposes that visual signal is processed in two ways. One, it's called the dorsal stream. The other is the ventral stream. The basic thing in the dorsal stream is the where stream. It basically guided the functionality. It's fast processing with low details. Okay? Now, on the other side of it, the what stream certainly is the recognition functionality. It has, it's slower processing, but considers really the higher details. And that's basically what people have talked about in neuroscience for a while. And to that effect, now if you go to a sensor, and the sensor in our case for the humans would be an eye, what we end up doing is what's called foveation. So what is a fovea? Fovea is a part of the human eye which captures the most details and responsible for sharp central vision, which is necessary in humans for any activity where visual details is of primary importance, just like the ventral stream that we talked about. So these are examples of some foveation where you can basically see that I can focus on this particular object and the rest of the things are blurred. So in other words, if I'm really focusing on you, I can almost blur out the rest of the image. I can actually change my glimpse size, and effectively it's more like the focal length change, though our eye focal length change doesn't happen much. So one can actually change the glimpse size a little bit, and I can actually have a broader view of the object. On the other side of it, we also do what's called saccades. Saccades are quick movement of the eyes between different fixation points. And human use saccades for scanning the surrounding and reading and so on, right? And this is, for example, recording the saccade eye movements of a participant looking freely at a picture. And this is again, a seminal experiment done some time ago, illustrating the eye movements within just 2 seconds, where, this is basically showing that, going from here to there, these are the eye movements that was observed. And again, those are the important points that the human was looking at in this particular case. So now the question is that can I really take this approach of the dorsal and the ventral streams, or in other words, foveation and saccades, to do better processing? So to that effect, and this is an example of an image that I'm showing, where I have, in this particular case, 3 objects, a dog, a human, and a cat. And so what I end up doing is I first take basically the original full HD image frame, minimize the details by reducing resolution, and then have a global context network that relies on foveation and mostly on macro saccades to really determine the points of interest. And in this particular case, the points of interest turns out to be, the cat, the human, and the dog. Now, what is also important to understand is the fact that you don't need a global context network. A lot of times we actually do random saccades. And we start at a point, start our glimpse, increase or decrease our glimpse size, and figure out what the object is. But in this particular case, we actually use this global context network, and this is an example of what can potentially be done if my glimpse starts right here, right? So for example, if my glimpse starts right here, at t equal to 1, what I can do is I look at it and try to figure out, hey, what is it? With a high probability, it's probably a cat's ear, so I'm priming my network in some ways. So if it is actually a cat's ear, then I probably would change my glimpse size, move top, down, and right, figure out, hey, can I really look for the eye of the cat? And then if I find that eye of the cat, I actually then go further, expand it down, and finally find out that, hey, that's the whiskers of the cat, and this is probably with a high probability it's a cat. And that's how I actually now come up with a bounding box for a cat. So for the fun of it, and this is actually what we did in our lab, my students actually experimented on these different images that they were taking at that time. And what I'm showing here is that, one can really figure out these bounding boxes of the face, determine which those individuals are for that image. Now this is interesting because now I can figure out multiple objects, and potentially if I can come up with the right way of doing it, my computation also decreases. Now what we also did is that this can lead to an interesting thing. Like, maybe if you do foveation and saccades, it turns out you can actually potentially think of, detecting optical illusions. If you give it to today's deep learning, what would this be? Who thinks it's a rabbit? Who thinks it's a duck? Yeah. Yeah, right. So actually you can prime the network that way. So interestingly, how many of you see both at the same time? Actually, ideally you should not be seeing both at the same time. You can't see both at the same time because your focus points are either going to be here, start with, then you see a rabbit. If it's here, it's going to see a thing. Not, but if you go back and forth, then it's okay. But otherwise, simultaneously, we don't. And that's why also today's deep learning is going to be completely confused. Right? So on the other side of it, if you really take that duck and rabbit situation, so it's either a rabbit or a duck, but not both at the same time. So what one can potentially do is that we did an experiment on that duck-rabbit thing. So if you start here, as you can see, we can prime the network gets primed inside the duck. Okay? And that's a bounding box for the duck. Now, if you start here, it forms the right glimpses now, and says, hey, it's a rabbit, and that's a bounding box for the rabbit. So if you give it to today's deep learning, it's going to be totally confused. No, we just wanted to actually have some fun, play with it, and say, hey, can you really do, these illusions? And illusions, in a lot of ways, we humans always try to find features. And as soon as we find features, we say, okay, that's what it is, and I can see that. So sometimes when you look at the cloud in the sky on a clean day, right, and somebody sees, oh, it's a dog. And somebody else says, hey, I see something else, right? And the reason why that happens is the focus point, the glimpses are different. And you're priming your network in different ways, and you're always trying to look for these features. Okay? Anyway, so when the drone is flying, if I give a duck and a rabbit, and if I say, look for the rabbit, then it can potentially find that rabbit and fly there, or potentially look at the duck and go there. At the same point, though. All right. So far, we talked about detection. A few other things that we have to do is tracking also. At the same time, we have to be able to track. If this duck-rabbit illusion or the duck-rabbit is moving, I need to be able to track it. So how do I track it? And this is an example of, showing that a car is moving, and I'm tracking the car. And again, different ways of tracking, but interestingly, and this is something which is very important to understand, that just by having one layer of spiking neural network, okay, with Leaky integrate and fire neuron, just one layer, and with a DVS camera, now you can track objects. And not only you can track objects, you can at the same time figure out the speed of the object. Not exact speed of the object, but maybe something which is moving between 40 and 50 miles per hour, 50 and 60 miles per hour, you can speed beam them in some ways. So that's something which is interesting. So to that effect, what we did is we actually take that approach. This was actually presented in ICRA last year, is what one can do now is, and this is an example of taking this, what we did is we actually had this DVS camera, and this is our drone. We wanted to mount the DVS camera on the drone itself, but this is an indoor environment. In a small indoor environment, we are not allowed to use bigger drones, right? And this DVS sensor is actually quite heavy. And so we couldn't really put it on this smaller drone. So we actually had to put the DVS sensor separately. Now what this sensor does is really figures out what's around it and figures out, hey, there's a moving object. And this particular case, the moving object is this ring. Figures out the neural network in the drone, figures out, hey, what's the speed of the object? Tracks that particular object, figures out the speed of the object, and then determines that, hey, I'm going to have to fly between this, through this particular ring and go and land on the other side. And that's the job. And as you can see that in this particular case, the drone now figures out that the speed of that object moving and then determines to fly at a particular time through that ring onto the other side. That's again using these hybrid neural networks. And the hybrid one gives you really low complexity networks, and that's what I wanted to underscore here. Better time for training, and at the same time, the number of parameters for some of these networks are much, much lower. And again, the reason why we're using spikes / DNN is really to take advantage of the fact that timing information is important, and if I can remember the past, it actually helps. Now, following such algorithms, you have to finally implement them in a hardware, right? And if you don't implement it in the right kind of hardware, you're not going to get the advantages. So what we've been actually looking at is, what kind of hardware is going to be good, what kind of devices does make sense to implement the neurons and synaptic operations, and should I really doing spike-based computation, or rather, should I do in-memory computation or not? And what does in-memory computing really means? So to that effect, we've been actually trying to also build hardware fabrics, and including actually looking at devices that can potentially, implement it more effectively. So we've been looking at circuits and architecture that can efficiently implement the algorithms and possibly embody the computing principles of the brain. On the right side of it is a chart from IBM showing, for different deep learning applications like speech, language, vision, the number of matrix vector multiplication or the matrix multiplication that you end up doing. So these red bars basically showing that, hey, most of the time my computations are all matrix vector multiplications. So is it possible that I can do better matrix vector multiplication? So what are the other operations that I end up doing? For example, if you have transformers, other operations that you end up doing are the softmax. You do end up doing good amount of softmax, right? You also end up doing, for example, sometimes exponential functions. But the matrix vector multiplication and these functions are the majority of the functions that you end up doing for, both spike-based computations or these deep learning. So the question, of course, is, should I do my computing in the memory itself? And why is that important? The reason why it's important is the fact that if you want to do computations, if you have to get your data from the memory into your CPU and then put it back again after computations, the traffic between the memory and the CPU is large. And in fact, that ends up taking a good amount of power consumption, if not the majority of the power consumption. And again, there are different levels of memory hierarchy. So if I have to go from register file to L1 cache or to the DRAMs, then it becomes really not so effective. Finally, a few other things that you can also do. I'm not going to talk much about that, but it's also possible to do approximations, right? And then the reason why you're able to do approximations is the fact that it's an error-resilient application. 10 plus 10 certainly is 20, but for all you guys who are graduate students, it doesn't have to be 20. It could be 19, or it could be even 21. And the reason why I'd like to make it 19, 20, 21, or whatever it is really because of the fact, hey, can I have a circuit, if I implement that as an approximate adder, that circuit is going to consume very little power consumption. Or in other words, I'm not maintaining the Boolean equivalence. If I don't maintain the Boolean equivalence, your arithmetic becomes interesting, but your circuits have to be really, really less complex. Now, of course, at the end of it, you're going to say that what's going to happen to me? If I do implement it in those circuits, my accuracy is going to go down. The answer is yes, it'll go down. But if you train it with those approximations in mind, then you can actually get back most of your accuracy. So in other words, you're not going to learn the data, but you're also going to learn the approximations. And if you can do that on the hardware, it turns out you can get it back. And we'll see that we can use some of those techniques. And finally, at the end of it, should it be event-driven computation? And I didn't talk much about the devices and the interconnects. Those are also very, very important. So where are we today? Multi-cores and GPUs and accelerators. But if I were to be able to do in-memory computing and some of these other approximations and all, maybe I can actually reduce the power consumption a lot. So with that in mind, I'm not going to talk about approximations. Well, actually, I do talk a little bit about approximations. But if you do that, you can actually get some interesting. How much time do I have? 5 minutes, okay. All right. So 15. All right. Somehow it has increased. So, all right. So what one can do is, I'm not going to take too long. So now, this is my standard memory, right? In a standard memory, I turn on a word line, right? I turn on a word line, and these are my bit lines in the memory. And once I turn on, I have these sense amplifiers, and I end up reading the data, right? Now, what I can also do is, I can try to turn on 2 word lines simultaneously. And in this particular case, I have a V1 and a V2 voltage. Now, if I turn on 2 word lines simultaneously, and don't try that on a 6T cell, if you do that, there's going to be a short. So those of you who are familiar with MEN memories and 6T cells, you'll end up having a short. There you have to do staggered activation. But if you otherwise, in an 8T cell, you turn on 2 read word lines, as an example, or for example, in PCMs and RMs, you can do it in a separate way. So if you can turn on 2 word lines, turns out that if I were to add a little bit of extra circuitry at the sensors, right? If I do that, I can do AND operations, OR operations, XOR operations, and so on, by playing with that sense amplifier in some ways and adding something extra. Now, once I'm able to do XOR operations, I can do also add operations. So if I have an 8T cell, interestingly, one can show, without going into the details of it, you can turn 2 read word lines, do an XOR operation. With some more logic, you can do addition, right? And now you can put it back into the another memory location by turning on the right word line. So in one cycle, you can actually do that. So those are actually interesting possibilities. It increases the complexity of these interface circuitry a little bit. And then you can be a little more greedy and say, hey, I'm going to turn on multiple word lines. And if I'm able to turn on multiple word lines, one can show that you can actually do a matrix vector multiplication, but in the analog domain. Okay? Matrix vector multiplication, so that really also means that I need my interface circuitry to be more complex. How much more complex? Depends on how many word lines I turn on at the same time. And it turns out it's going to be the problematic one, because it's going to be an analog to digital converter. Because you don't want to communicate in the analog domain, because your analog noise is going to kill you. So now you want to communicate in the digital domain, but that computation is going to be analog. Can you do that with non-volatile memories? The answer is yes. It's simple to do that in non-volatile memories. You can do it within SRAMs. But also, we can also embed our ROM into a RAM at no extra cost. I'm not going to go into the details of it. So that can do transcendental functions. Because I can have a ROM, rather than a DRAM, I can have a ROM embedded into it at no extra cost. And I can actually do exponential functions. And then once I'm able to do exponential functions, I can do sigmoid, I can do tan hyperbolic, or I can do the softmax. And these are the colorful devices one can potentially use. Okay? So what are these devices? I'm not going to go into any details of any one of these devices, but these are a little more mature devices that we've been actually looking at. A ferroelectric transistor. This is basically a magnetic tunnel junction with a heavy metal PCMs and RMs and so on. These are even more exotic, so I'm not even going to talk about it here. So each has its own kind of advantages and disadvantages. CMOS is still very good. It is good read, good write, good endurance. PCMs don't have very good endurance. RMs don't have very good endurance. MTJs certainly have much, much better endurance. But write time is larger than certainly CMOS. So what one can now do is, using one of those fancy devices, one can do, for example, a crossbar-based computation like that, where I have these inputs which are V1, G's are the conductances, and if I do that, I'm going to get a summation of VI times GI, which is basically going to be my dot product, right? And devices could be any one of these interesting devices, including CMOS, but remember that the interface is going to be important. When I turn on multiple word lines, my ADC, and if you have a 7 by 128 cross 128 crossbar, then you need, for 1-bit implementation of it, you need 7-bit ADC. And 7-bit ADC is going to cost you. Okay? But also remember that there's enough sparsity usually in the design, so you can reduce the ADC cost by using sparsity. And then you can put all these devices together into a larger scale design using an NOC. I'm not showing the details, but it would look somewhat like that. Somewhat like this, where you can put the things together. These are matrix vector multiplication cores, but you need some standard shared memory, some glue logic around it to be able to do these computations. So anybody wants to try it, it's actually a Puma architecture that we developed in collaboration with HP. It's available in the GitHub, and you can actually use the different kinds of devices to do that. Problem with all this is that your ADC is going to be the bottleneck. Area taken up by ADC, energy taken up by ADC. Still better than the standard von Neumann computation, but really, if you can reduce your ADC cost, that's much better. So to that effect, actually, we've been looking at different kinds of hardware, and this is an implementation of optical flow in NVIDIA Jetson. What was interesting to note is that when we implemented optical flow, we wanted to actually have about 30 frames per second. And what we found in that Jetson, it was about 7 to 8 frames per second. So definitely not able to meet that demands. Here, this is basically our design of an in-memory computing, which I didn't talk about, in a 8T CMOS cell, and considering sparsity and everything. And it turns out that can actually do about 35 to 40 frames per second. This is a spiking network architecture that we designed, again, in a 65 nanometer technology. And that can also actually give you the kind of performance that you'd like to have. And again, these are all doing in-memory computation. What's the difference between the spiking and this one? That this one actually has memory and potential, which is also computed in memory. Okay? And finally, ADC was the bottleneck. Can I get rid of the ADC? So we actually looked at the possibility of having a completely ADC-less design with just sense amplifiers. So what's the catch? Remember approximations? So we talked about this quantization. Now you have to train it with that in mind. Otherwise, you're not going to have accuracy. And if you do that, you can get back your accuracy. So this is an example of this implementation of this in-memory computing architecture that we did. Still, bottom, turns out that the power consumption dominated by the ADCs, but certainly can give you about 1.4 to about 6 TOPS per watt in this particular case for 4-bit computations. This is basically the spiking architecture chip in a 65 nanometer technology. Again, I'm not spending much time on it, but what I really wanted to underscore is the fact that by getting rid of the ADC, one can potentially get a huge amount of improvement, but you really have to do this partial sum quantization about training. And without that, you're not going to have the accuracy. Again, not showing much of the results here, but it's possible to maintain the accuracy. And showing that if you have an ADCLS design now, for a spike flow net, remember the optical flow architecture that we talked about, it's possible now to get a good amount of improvement, 35 to 70x compared, and this is a simulation results, not a 65 nanometer TSMC implementation that we had, but about much better than the Jetson implementation that I showed. I'm not again going to spend time, but there's a need to think about, if you have to really design that to be a new modeling and simulation techniques and EDA tools required to do that. And finally, just to end, I assume that I'm within my time now. Here's some parting thoughts. I believe that for the kind of applications that we're looking at, sequential applications, and in fact vision-based sensing, turns out that these bioplausible networks with these hybrid sensing techniques can potentially be quite effective. Can give you much lower parameters and these hybrid networks makes you training also simpler than training a full-scale spiking neural network. Good amount of potential for edge computing. I didn't go into much details of it, but in the future there's possibilities of using some of these neuromimetic devices that can mimic the neurons and the synaptic operations more effectively. Those can potentially be quite interesting and important. And finally, at the end of it, the take-home message that I really feel it is going to be important is that algorithm hardware co-design, guided by biological principles, can be the pathway for the next generation neural computing. All right, that's all I have. Sure. Yeah, I actually forgot to mention. So these are the guys who make things happen in my lab. These are the current students in my lab, and they do all the job, and I go around the world, giving lectures. Thank you.
Thank you. Let's thank Professor Kaushik Roy again for a fantastic talk.